In this video, we're going to be explaining how we connect physical to logical system decompositions. We'll explain why the logical system decomposition is helpful in your model, and we will show 4 different alternatives. Alternative A, B, C, and D. Alternative A being the simplest, and then we will get more and more complex. We'll show several different examples of tables that have special columns that can show the connection between the logical and physical. So with that, let's go ahead and get started. In your model, you're going to have to make some decisions, such as, do we need to have a logical decomposition in our model at all? And should we model the logical and physical on the same block, or should we have 2 separate blocks, one logical and one physical? So we have 4 different options here of how to model each of the physical and logical decompositions. And we've got the pro and cons list that you see here. So what we need to do is make sure that our solution, our option that we like, is going to be able to handle several simple and complex implementations. So the simplest implementation would be a one-to-one mapping between your implementation and your logical decomposition. So what that means is that there's one-to-one relationships between your logic and your physical. There's a cable here that's going to essentially send the logic from this connector up here. The more complex example is the harness split, and that's going to be, so your logic is going to remain the same, but instead of having like 2 ports, you're going to have one connector here, and that connector is going to have a harness, and that harness is going to flare out to P1 and P2. Finally, we have our pass-through implementation, where we are trying to get subsystem C signal to subsystem C and the to subsystem B signal to subsystem B. But to do that, we're actually sending the subsystem B signal through subsystem C to get to subsystem B. So there's not a direct connection from subsystem A to subsystem B. That's what we mean by pass-through. So all of our different logical to physical mapping or solution or alternative that we're going to show needs to be able to handle all of these different implementations. So now we'll jump through each of our options. So we'll start with the simplest option, and then it'll get more complex as we go down. So the option A is just going to be to modify the logical into the physical. And that's pretty straightforward because there's no mapping between logical and physical, because there is no logical in your model at the end state. The only way that you would be able to access the logical aspects would be to revert back to a time in the model where you actually had that logic. Now, this is not going to be a good alternative most of the time. Most of the time, you're going to want to be able to have that logical decomposition. And that's because if you ever create a version 2 of your product, you want both version 1 and version 2 to trace back to the logical decomposition to make sure that it meets the requirements. And you want to be able to compare version 1 and version 2, do some analysis of alternatives. So you're going to want long-term to have that logical decomposition. But if you're in a bind and you need just the physical implementation for some reason, then this could be a good short-term solution for you. We're going to move on to option B, which is much more complicated, and we'll look at just the straightforward method first. So that's going to be your simple map, and we'll jump into that right now. So up at the top, this is going to be your logical view IBD, and then this is going to be your physical view IBD, and essentially they are all having the same context. So the system block right here is both logical and physical. And what that means is that you actually are going to have this cable 1 and cable 2 that are going to be added as physical entities alongside or as part of your system block. You can then show them in your internal block diagram and then mount them to the connectors that you see there. You could also add the reference properties underneath your proxy ports. So P1 is typed by P1A. So if I look inside of here, P1A, this would be a logical proxy port. It has the reference property electrical connector of type connector P1A. So this connector P1A would live right here. This is a physical part and connector. So this guy is actually like the part number that you would purchase. It's talking about the physical thing, while this is talking about something logical. So essentially we would connect this electrical connector as part of the cable, which would then connect to the other connector at the P1B side. So this would be your physical view of your option B. So then you could essentially have this table down here created, which tells you the block that it starts with, the port which it's going over, the reference at side A. So this would be the connector at the port of side A. It's going to tell you the role, the connector itself, name, where it's going, the mounted element, so what physical cable is going to be housing the conveyed flow of the to subsystem B signal, and then you can see where it goes to port B. So this is the logical, this is the physical, and then this is the physical block. So you can show all of that on a single table. Now moving to option B, this is going to be the harness split method. That's what you're seeing here. And so again, our logic is the same. We're using the same system, logical and physical block, and this is what it would look like. And this is a little bit more confusing to me because you still have two logical blocks, and it appears just on first glance that this electrical connector is different than this electrical connector, when in reality we're trying to show that there's only a single electrical connector on the subsystem A side, and then it jumps out to subsystem B and subsystem C. So for me, this isn't as clear, but it does still like work. It's from a table perspective, it looks pretty clean, but I don't think from a physical perspective it's super robust. Now moving on to the last one, which is the pass-through method. The pass-through method is where you start to have some confusion arise. And so this is what we're trying to show. Now this was copied from one of the diagrams up here. So you would not be able to see this if you went with this modeling method, option B's modeling method. So you're going to be seeing this, which is very confusing when this is pretty simple. So you have cable 2, which would be essentially this guy right here, and then cable 3, which would be this guy right here. But it's hard to convey what's physically happening with what we're seeing here. So I don't love this method by putting logical and physical together if you're going to have this pass-through implementation. So this is definitely a weakness with option B. So now we'll jump to option C in the hope that we can make a solution work that has the pass-through. So this is option C. As you see here, we still have the logical and physical system block that is one and the same, just as option B. But what we're doing differently is we have different proxy ports, one for logical and one set for physical. The blue is logical, purple is physical. This was created by using a legend and creating a rule for that legend. I went ahead and just added physical and logical stereotypes to each of my proxy ports to differentiate. So that enables us to then show IBDs with the same context, the context being the system, logical, and physical, but you could have a logical view, you could have a physical view, and you could also have the both view, which is going to show you the relationships between logical and physical. We added relationships, the refined relationship between proxy ports, as well as between connectors. We can look at several new tables that we created. This ICD table has several custom columns. So within the system context, because it is one block, we're going to have both the logical and the physical. So you can filter based on just that one first column, logical. So I'll set it to true. And so now it's filtering the logical entities. If I set it to false, it will do the same for my physical entities. I'll show them both right now, and you can see that we have the harness, which is being applied using the mount relationship to the connector, which is the element type that we start with. Some people would like to see it in terms of like everything from a specific subsystem or context. So this one, the element type is the proxy port, and the scope is subsystem A, subsystem B, and subsystem C. So essentially we've added another set of custom columns here that allows you to see just about every single relationship that you might want to see. And you could certainly descope this from just subsystem A, subsystem B, and subsystem C just to a single subsystem like that. And now you're seeing all of the logical and physical connectors which are coming out of subsystem A and going to other subsystems, such as subsystem B and subsystem C. Now to assess option C, it's good and bad because it uses this single logical and physical block. I would say in most cases, if your system of interest is very complex, it makes sense to separate the logical and physical decompositions. But if your system is not super complex, it may make sense to just have them all on one block. You're just going to have a lot of complexity as this scales. Additionally, if you look far down the road, you may end up having multiple physical implementations instead of just a single implementation. If that is the case, it's not going to be too hard to copy and paste the entire system, logical and physical, and create a new implementation. But the problem is with that is now you have two logical sources of truth. One of them will be the logical source of truth for the first system that you've created, while the second decomposition via copy-paste would create a second logical source of truth. So you're going to have to decide if you want two separate logical sources of truth, or if you'd like a singular source of truth for the logic. And the way to do that is to keep them completely separate like you would in option D. We'll look at that now. In this method, we're going to have a logical breakdown that could live in a logical package, and this is how it would look right here. We're not going to build out the single map because it's so simple, so we're only going to focus on the harness split and the pass-through. So the physical implementation 2 here is going to be talking about the harness split. So in our physical implementation, we're going to have our harness that is then mounted to the different connectors. And then we will actually create this new block right here, which is going to allow us to create an internal block diagram to make the mapping between physical to logical. So the parts of this logical to physical implementation 2, which talk about the harness split, would just be the logical system, this guy, and the physical system. So when we jump into the IBD of this, you'll see we have our logical system up here and our physical system down here. And we can then refine relationships between the proxy ports and the connectors. We can then add tables to then show the relationships between logical and physical. Note, you could certainly come in here and just change this to subsystem A, and so now it's showing all of the connectors that are coming out of this subsystem A through the different ports. We only had one port, so that's why you're only seeing one row, and how it connects back to the logical. You could absolutely do the logical as well here, and then you could add in your columns that we showed before on option C to show the different physical entities that are connected to the logical entities. For this example, we're just showing all 3 of the physical subsystems and then how they connect back with their logical entities. If we look in this table here, all of the same options or custom columns that were created and shown in option C could totally be shown within this example. We can filter it or rescope it however we see fit. We just kept it simple by showing the, I guess, more complicated custom columns within option C instead of option D. But you could absolutely copy it and do it here, no problem. Now we'll jump to looking at the logical to physical implementation 3, which is going to be the pass-through method. So you'll see we have cable 1 and cable 2. Cable 1 is going to be mounted to this connector. Cable 2 is going to be mounted to this connector. And we can go into the logical to physical and see all the relationships, the refined relationships between the proxy ports and the connectors. And then we can tabulate that as well, just as before. There's no issues at all. It's pretty clean, and this is definitely my preferred method, but it does require a little bit extra setup because you have to create these blocks, and it can be a little bit confusing to your customer to have different system decompositions, not all associated with one block. So this is definitely the most scalable method that we have shown so far, and my preferred approach. Note, the option D does not require the proxy ports to be typed logical and physical because they have different contexts. So it's pretty obvious that all the proxy ports that are going to be on the physical system implementation would be physical, while all the proxy ports that are on the logical decomposition are going to be logical. We might create another video to help explain how to create all of these custom columns, as well as the customized rules that would be used for the legends. So look out for that. Please recognize that options A through D is not an exhaustive list of different ways to model the implementations. You could absolutely not use this mount relationship. You're not forced to use the refine relationship. You could use different association blocks or different relationship types. We're just showing a way to model the physical and logical and connect the two. We're trying to explain the different alternatives that you have, the pros and cons to each alternative, and figure out what decision points you have so that you and your team can create the best architecture for your system of interest. Hope this example helped.